since my colleagues on MASSTART have in length presented the challenges of data center interconnect so far, I'm going to focus on our ioNext offer, which is, well, as the title indicates, a glass-based platform, so passive photonics, as we'll see, that we hope can leverage synergies with active platform like Silicon Photonics. So a little bit of corporate background. So we are located in Grenoble, France, quite close to CEA-Leti, in fact, of which some of our technologies come from. So the company was incorporated around ioNext, this ion exchange waveguide on glass, but after the telecom crash in the year 2000, switched to Q-switched microchip laser business, which still accounts today for most of the revenue. But recently we've restarted the photonics, the glass-based photonics product line to basically foster the effort, also the industrialization effort around Silicon Photonics. So the first WAFTs were released and sold in 2016. We'll see what they are, these interposers. And we hope that this year we will be able to release our first PDK for passive photonics. So that's basically what we offer. So ioNext stands for ion exchange. We'll see in a few seconds what it means. But basically we can offer passive circuits on glass because, of course, so far it lacks active functions. But as we'll see, leveraging a very good matching with optical fibers and low loss all over the circuit. So as of today, here is the kind of functions that we can offer, like splitters, evanescent couplers, mode converters, and some derivatives like MUX, DMUX, basic interferometers, and waveguide crossing that can be quite convenient in terms of footprint. So what is ioNext? Well, basically it's a pure glass photonics. So it's close to PLC, to planar lightwave circuits, but involves no etching. So we start from an old silica wafer. It's a proprietary glass melt close to SiO2. We deposit an aluminum mask on it, and through a photolithography step, we make openings where we want the waveguides to be created. And after this step, basically we step out of clean room. So it's after that, the steps, the ion exchange steps to dope the waveguides are quite low tech and low cost, I must say. And all of these guarantees like good valued chips and a short turnaround time, around 1 month from the GDS to the chips actually. Following these ion exchange steps, we have some capability for dicing, pigtailing, and packaging. So the added value, I would say, is the usual one for glass, so large optical bandwidth. We'll see that we have an offer for visible wavelength and another one for infrared ones for the telecom band. Propagation loss is low, of the order of 0.1 dB per centimeter. The PDL is low as well, which can be nice for instance, for coherent transceivers. It's not written here, but our waveguides are polarization maintaining as well, pretty temperature independent. On top of that, we'll see that we can at the same time offer rather low coupling loss with optical fibers, rather compact devices. Of course, it doesn't compare with Silicon Photonics because the index contrast is clearly not the same, but we have some tricks to go around that. So basically, those tricks that we call 2.5D waveguide engineering sums up to our spot size converters on the facet. We can very well match the SMF28 fibers or PM fibers mode field diameter on the facet for bad coupling, and we reduce the mode size to about 4 by 3 microns. We'll see that it can be used in two ways, either for interposers, this WAFT series to match Silicon Photonics spot size, or to realize these compact circuits on glass. On top of that, we can slightly modulate the depth of our waveguides. So usually our waveguides, they are buried, they are passivated and buried under our substrate surface, but we have room to keep them at the surface So once again, can be used for interposers or for surface sensing, even though we're getting out of the data center topic here. So what is used in MASSTART, and more generally, what do we offer around Silicon Photonics? So it's mostly this WAFT that stands for waveguide arrays to fiber transposers. So we have three solutions, one for edge coupling, so which is compatible with the WDM, rather low loss. Unfortunately, wafer level incompatible and rather demanding in terms of alignment. We have solutions for top coupling, so basically sending light through grating couplers, which has some pros and cons once again. But overall, like, it's quite limited in terms of bandwidth when we speak of WDM. And we have a more experimental solution, I would say, that we call evanescent coupling. We'll see in a few slides what it means. So edge coupling, basically, the offered value is at the same time spot size conversion. So as I've said before, we can go from a fiber array with 10 micron spot down to 4x3, which is quite nice. For instance, in the MASSTART case, the Leti tapers are pretty well matched through this mode adaptation. And if for high port counts projects, we have the possibility to concentrate the optical ports, as we can see on the picture below for one of our former customers, which can be quite nice for projects where with high fiber counts, like switching or very high speed optical transceivers. In terms of insertion loss, since there was a question about it, so we generally guarantee an insertion loss of about between 0.5 and 1 dB from the fiber connectors to the WAFT facet, so basically to the Silicon Photonics PIC facets here, even for a large number of channels. And then, of course, the coupling loss to the PIC itself depends on the spot size converter technology that is used on it. But we've measured on MASSTART that it can be, in average, below 1 dB for quite large port counts. The TC-WAFT has more or less the same philosophy, except that here there is no spot size conversion. The idea is just to concentrate the ports and to have a low profile solution, unlike fiber arrays, for instance. So here the WAFT has an angled tip with a mirror deposited on it that basically deflects the beam towards the grating coupler, which means that we can have an assembly that is only a few millimeters thick, which is not possible with bent fiber arrays. Another application that is explored within MASSTART is to use this TC-WAFT with a confined mode, this time to probe the PIC at the wafer level. So basically, Leti uses trench to access the grating couplers, and the idea would be on a probing station to use this TC-WAFT to come and test the functions, the Silicon Photonics functions, before dicing the wafer to evaluate the process quality. Last solution that I mentioned is evanescent WAFT. So this was suggested by a customer. Actually, it's ST Microelectronics. It's because they've published about these results. So the idea is here to use direct evanescent coupling between our surface waveguides on glass, as figured here on the bottom left, and the nitride layer on the silicon PIC, which actually has quite a few advantages. It's broadband, single mode all over the O band and C bands. It's quite low loss, as they've shown. It's low PDL, and it's rather alignment tolerant. For instance, as we can see through the WAFT, you could use quite easily passive alignment via fiducials on a machine, an automated machine with some machine vision. Of course, the drawback of this is that you have to etch away the BL here to remove the cladding, oxide, and the electrical contacts where the WAFT will interact with the PIC waveguides. So here they've made some measurements. I will not spend too long on this, but they have made some tolerance analysis on this coupling method. All right, just a slide to say that since we started in the FTTH business with splitters back in 1998, we have had a long experience of fiberizing our chips. So this can be nice for customers that are not too used with photonic packaging. MASSTART, on top of that, has given us some experience when it comes to aligning and coupling WAFTs to other chips like silicon or 3.5 lasers. These are among the leads that we explore within the project. So even though this is manual alignment for small volumes, we're establishing partnerships to offer assembled WAFTs and PICs on larger scales through partnerships with automated capabilities. So a slide once again to mention that we offer interposers, and that's really our main focus within MASSTART. In this project, we are tasked to increase our production capability by strengthening our fabrication process, but we want to be a bit more than that as well. So as I said, we are developing two process design kits, one for the visible wavelength, one for the near-infrared wavelength, where we want to ultimately to work with design houses and to be able to offer multi-project wafers and embed more functions on our glass chips than I would say only spot size and pitch conversion, pitch matching. So this can take multiple forms. We are strongly hoping to explore the realization of AWGs on glass, like polarization independent. This is something that Teem demonstrated in the past and that we are to I would say revive. On top of that, we've demonstrated some hybrid assemblies with our proprietary erbium doped glass, so assemblies with passive chips, DFB lasers, amplifiers, lithium niobate modulators, all of these that could nicely go around the Silicon Photonics project, especially when we talk of onboard optics in that case. And with this, I would like to thank you for your attention. Thank all the partners within MASSTART. It's actually very valuable for Teem in terms of applicative knowledge and access to high-end technologies and skilled partners on this project.